talk is John Gore. Talk about Nucleon-Nucleon Bremsstrahlung in supernova matter revisited using chiral effective field theory
Good afternoon, everyone. So in this talk, I will talk about using chiral effective potential to revisit the nucleon-nucleon neutrino emission in this process. So first, I want to say something about the vision, so why I want to start this process. And in the second part, I talk about more details about how to calculate this, the nuclear potential, how to choose nuclear potential, key metrics, and then I will discuss the results. So, massive stars, typically they will end their lives with a collapse of the core, which is then followed by the explosion. And during this process, neutrino process actually plays a very important role. So actually, it's the neutrino that drive the shock and make the successful explosion. So neutrino induction in hot dense matter play a very important role. And besides that, they also determine the final neutrino signals arriving at Earth, and also the synthesis of heavy elements in this object. So we need to have a very accurate calculation of this process, all the neutrino process. And in this talk, I will only focus about on one specific process, the neutrino pair process, either pair absorption or emission from nucleon-nucleon neutrino. So here I showed the diagram for this. So Na, Nb, either a neutron or proton. So they interact with each other with some nuclear force, and meanwhile emit a pair of neutrino, anti-neutrino via the exchange of Z boson. I think the trivial part is about the neutrino coupling to nuclear. So this is very trivial and perturbative. And the non-trivial part is about how to describe the nucleon-nucleon potential, nucleon-nucleon interaction part. The other aspect is that, so I think now this is becoming more and more popular that people use the coning of neutron stars or the supernova matter to constrain the new particle emission, to constrain the property of new particle like dark photon, axion, also some dark scalar, and also dark matter. So basically, we need to replace the neutrino pair by axion, dark photon, or a pair of dark matter, anti-dark matter. So to get an accurate constraint, we also need to know how to better describe the nucleon-nucleon interaction part. So this is basically my motivation for this study. So in the following discussion, I will only focus on the neutrino process, but the discussion basically applies equally to new physical emission, new physical particle emission. So here I show all the 8 diagrams. So basically, the neutrino pair can couple to each nucleon line. So there are 4 options, and the left 4 shows the direct contribution, and the right 4 shows the exchange contribution. So the sum of those two gives M1, the amplitude M1, and the second law gives M2, M3, M4, and so on. So we sum them together. So maybe I can explain more details about this. So V is basically the nucleon-nucleon potential. Sigma means the neutrino coupled to the spin of the nucleon. And A, B, C, D is for the initial 2 nucleon and final 2 nucleon states. Omega here is the propagator of the virtual nucleon. And Li is for the leptonic weak current. Here we have coupling constant for neutrino Ga, and also Gf is the Fermi coupling constant. So we sum those 4 amplitudes together, we get the total amplitude, which can be expressed like this. So here I basically ignore I only include the x vector terms, which means neutrino only coupled to the spin of the nucleon. I have ignored many higher order many body interactions. So basically they can contribute like 10%. So the key point is about how to choose for the potential between the nucleons. So we have some options, and the most simple one is to choose the 1 pi exchange potential, which is also denoted as OPE. So this is not the operator product expansion. So in nuclear physical community, we call it OPE. OPE refers to 1 pi exchange potential. So it's basically induced by exchange of 1 pi and between two nucleons. So a better choice is to use the more modern force, like carrier effective potential force. So basically, the Hamiltonian can be built from spontaneous broken carrier symmetry. And the nuclear force can be constructed and can be viewed as an expansion in terms of Q over number chi. Q is the typical energy for the dynamics. And number chi is the energy symmetry breaking scale for carrier symmetry. So it's an expansion of this term, and the coefficients can be fitted to scattering data. Actually, so we have very precise emergent scattering data for nuclear neutrons. So here I show each diagrams. They contribute to the nuclear force at different levels. So here is the leading order contribution. Then we can also include the high order contributions. So to reach a desired accuracy, we only need to include a finite number of diagrams. So this is the good point about nuclear force, about carrier effective potential. So 1 pi exchange potential, they contribute to the leading order. And compared to 1 pi exchange potential, we also include some higher order terms in carrier effective potential, like the contact terms, and also some multi-pi exchanges. So they basically contribute to the short range parts. So to calculate this process, both the OPE and also the carrier potential at Bohr level is not enough. The reason is that nuclear force is non-perturbating. So that's the reason we need to go beyond Bohr level and introduce T matrix. So T matrix basically gives the full amplitude for nuclear scattering. So to understand it simply, so it's basically a sum of an infinity number of ladder diagrams like this. So by doing that, basically we include all the possibilities so that the nucleon can interact with each other by an infinite number of times. So when we put all the diagrams together, we get this one. So this is basically the so-called Bremsstrahlung equation. So the G matrix on the left-hand side is given by the Bohr potential at the leading order plus this term. So basically this is U. U gives this. And this is propagated for the two intermediate particles. And here we need to multiply the T matrix. So we solve this iteration equation, and then we can get the T matrix from the U. So for nuclear scattering in vacuum, the two initial nucleon and also the two final nucleon, they are all unsure. By that I mean they follow the energy momentum relation like this. So E is equal to k squared divided by Mn. So this relation is in the reduced system. So E is the reduced energy for the two nucleon, and K is the relative momentum for the two initial particles. K prime is the relative momentum for the two final nucleons. So if they satisfy this relation, then we call the T matrix unsure. However, for Bremsstrahlung, because we have additional energy momentum exchange with the neutrino sectors, so the two intermediate nucleons are not unsure. So they are generally offshore. And the final side, they are unsure. So we call the T matrix between offshore nucleons and the unsure elements, the half offshore T matrix. So this is what we need to calculate the Bremsstrahlung process. So it's a bit different from the vacuum scattering case. So in our study, we also take the so-called non-wavelength limit. So basically, we only include the energy exchange with neutrinos. We ignore the momentum exchange. And actually, non-wavelength limit is quite a good approximation within 10%. So to summarize what the potential I want to take, is basically I will use the T matrix solved from the Bremsstrahlung equation based on the carrier effective potential. So besides the so-called vacuum T matrix, we also calculate the immediate T matrix. So the difference between vacuum T matrix and the immediate T matrix is that. So when we solve the Bremsstrahlung equation, so here this is for the vacuum case. When we want to solve the immediate T matrix, we basically need to include the blocking effects for the two particle propagator. So if we include the blocking factor, then we can solve the immediate T matrix. So we want to compare our T matrix results to the rates based on the one package potential and bond number, and also want to compare that with the so-called unshared T matrix, which I will compute later. So to demonstrate my results, I will consider typical supernova conditions. So the temperature is given by this relation. So it's proportional to the density to the power of 1/3. And the density of the region covered in our discussion ranges from about 10 to 11 to 14 grams per cubic centimeter, which in barrel density is from 10 to -4 to 10 to -1 Fermi per cubic centimeter. So point Y is basically close to nuclear saturation density. I will basically talk about the inverse nuclear Bremsstrahlung process. So basically the prior neutrino absorption on two nucleons. I will calculate the neutrino, the inverse mean free path of neutrino or the neutrino opacities due to the prior absorption. Here I introduce the energy average. So basically the opacity should be a function of the neutrino energy. But I also do an average of the neutrino energy by simply assuming all the neutrinos following a Boltzmann distribution. So here I use Boltzmann distribution for neutrinos. So here I show the opacity or the inverse mean free path based on different nuclear potentials. So the black curves for using the vacuum T matrix, the red line for using the immediate T matrix, and the blue lines for OPE. And I show it as a function of density and also for different YE. So I forgot to mention the definition of YE. So Y is defined as Y is simply the proton fraction. The number of protons divided by the total baryon numbers. So for neutron-rich matter, YE is basically smaller than 0.5. With the basic result is that at low density, the T matrix gives rise to an enhancement of the rates. And at a high density, T matrix lead to a suppressed rates. So the reason is that at low density, because we know the nuclear force is resonant, so resonance need to be stated as an enhancement. And this cannot be described well by the OP potential. And it goes to the high density region, we have a suppression. The reason is that in the T matrix we include the short region forces. And this part basically has been ignored in the OP potential. So when we compare the media effects on the T matrix, this is simply about 10%, which is not very big. So so as I mentioned, we need to use the half of T matrix to calculate the Bremsstrahlung process. But if let's say the half of T matrix can be approximated by the so-called unshared T matrix using an average radiation momentum. So Ki, Kf are the radiation momentum for the initial two particle and the final two particle. So if we use an unshared T matrix with an average momentum, which is defined like this, then basically we don't need to solve the T matrix. We don't need to solve the differential equation because the unshared T matrix can be simply extracted from nuclear scattering data. So this plot shows the ratio of the opacity using unshared T matrix to that based on the half of shared T matrix. So we find that the unshared approximation is not good enough. So at low density, we have underestimation, and at high density, we have a slight overestimation. So this is okay. These are basically related to the behavior of the T matrix, varying with the momentum. So finally, I want to show the effects of blocking. So when we calculate this process, if we are allowed to ignore the blocking of the final two nucleons, then our calculation will be largely simplified. So here, I show that, ignoring the blocking of the final nucleon will be a very good approximation if the nuclear matter are in the non-degenerate region. But finally, it's not the case. So the ratio is defined as the opacity without including the blocking to that including the blocking. We find ignoring the blocking overestimated rates. by roughly about 20 to 80% on different densities. And we'll also find the effects are basically very insensitive to the nuclear force we use. The reason is that ignoring the blocking you simply to suppress the phase space of the final nucleus. So you should be independent of the nuclear force we use. So besides the T matrix that we use to describe the nuclear parts, we also studied another many body effects, the so-called random phase approximation effects. So RPA is basically to squeeze the vertex between the nuclear sector and also the coupling between the nuclear and the neutrinos. So in the non-gradual diagram, the squeeze the vertex is given by the bare vertex of the leading order, and also a sum of an infinite number of diagrams insertion of rings, the rings of particles and holes. So here I show the effects of the RPA, and actually I define the ratio of that, considering RPA to that result. I plot the ratio for different density and different YE, and even close to saturation density, the effects of RPA is basically below 10%. So which means so for the most cases we can ignore such effect. Okay, I come to my summary. So compared to the one-pair exchange potential T matrix due to enhancements and low energy due to the resonance property, and a separation at a high density due to short reading cost, and the difference is about a factor of 2 or 3. And compared to the unshared T matrix, half of shared T matrix gives enhancements and low density and suppression at high densities. And the poly blocking is very important, and it could be as high as 60%, as close to saturation densities. And we also explore the RPA effects, and we find it's basically quite minor. So actually, when we finish our calculation of the Bremsstrahlung rates, there are some groups try to use our rates in the real supernova simulations. So we hope that they can find some effects in the neurons. Okay, thanks.
The Z could also come out from change pi.
Excuse me. Z coupled to pi. Okay, so this is basically this is basically many body current. I have ignored. So the pi can also couple to the Z can also couple to A.
Yes.
I have ignored this contribution. Yes.
You know it's important.
So in nuclear physics, so in nuclear beta decay, people have estimated this effect, and they claim that the effect is only about 10 to 20%. So I suspect it's not important in our case.